as you know, it's one of the four main fields of content at the IMO besides algebra, combinatorics, and number theory. And so usually every year there would be one or two topics on the topic of number theory. And so I'll talk about some topics related to number theory, but it's a pretty big field. So the first thing is something you probably already know, which is that, you know, a number can, any positive integer, and so yeah, number theory is pretty much the study of the set of integers and their properties, especially as it relates to prime numbers, are particularly important because of this result that you probably already know, the fundamental theorem of arithmetic, which basically tells you that, you know, any positive integer has a prime factorization in a unique way. So, you know, for example, like 2020 is 2 squared times 5 times 101. And, you know, those are all prime numbers because they're not divisible by any other positive integer except themselves and 1. And we say that 1 is not prime. For, you know, 2021 is 43 times 47, or 2017 is just prime, or 1, we would say just like no primes at all, just the empty product, whatever. And so, yeah, that's sort of the most fundamental result about prime numbers, because it sort of tells you that prime numbers are sort of the building blocks of everything else. And so, sometimes, so prime numbers are, you know, very important, but sometimes, you know, you want to use their properties. But yeah, there are more results I want to talk about also. So yeah, I also wanted to talk some about like modular arithmetic, which I'm told y'all have already seen some of, which is good. Because this can, you know, it's pretty hard to get a handle on if this is your first time seeing it, but if you've seen some before, it's, you know, easier to get. And yeah, so basically modular arithmetic is this idea of, oh, and by the way, if there are any questions at any point, feel free to put them in the chat or ask them out loud. I want to be sure to, you know, answer questions if people have them. So yeah, feel free to ask questions. So yeah, modular arithmetic is basically this idea that if you have some positive integer, e.g., say d is, you know, 7, then there's sort of this idea that you can sort of say that two numbers are equal if they differ by a multiple of 7. Like, you know, you can imagine a clock, and like every 24 hours, it tells you the same time as it did 24 hours ago. So like, you know, every day, it sort of is on a 24-hour cycle. So two times that are, you know, 24 hours apart or 48 hours apart or 2,400 hours apart, it sort of still seems like they're the same time if it's 7 p.m. on one day versus 7 p.m. on another day or something, even if it's not actually the exact same time. And so this is that same idea, but you could do that for any positive integer. And this has a lot of nice, useful properties because it respects basic arithmetic. What I mean by that is that, like, if A and B are congruent modulo D, and C and D are congruent modulo D, then like the sums are congruent, and their differences are congruent. Oh, I guess I shouldn't use D for that. X and Y. And their products are also congruent. Now, their quotients do not necessarily have to be congruent. But so you could have something like, what's a good example? Okay, like you could say, for example, modulo 6, you have 16 is congruent to 34 mod 6, and 8 is congruent to 2 mod 6. So, you can say 16 plus 8 is congruent to 34 plus 2. But you can't, and you could say that about their differences and about their products. So, 128 is congruent to 68 plus 6. But, 16 divided by 8 is not congruent to 34 over 2 mod 6. 2 is not congruent to 17. So that's sort of an example. And while I'm mentioning basic properties, I think I should probably mention, there are some basic properties of prime numbers that don't involve this modular arithmetic or anything, but are still important to know, or some properties that are just more or less basic algebra, which is sort of related to this modular arithmetic stuff. So if two numbers are both divisible by some number, then their sum and their difference are, if D divides at least one of two numbers, then it divides their product. And another thing, which is if a prime number divides the product of two numbers, then it divides one of them. And you can sort of just see this by looking at their prime factorization. This last thing you can see just by sort of looking at prime factorizations. If neither of them were divisible by p, then you could write out their factorizations without any p in them, and then when you multiply them, you still wouldn't have a factor of p. So yeah. How am I doing on time? Okay. And so yeah, I'm going to show some example problems about this stuff, so don't worry. And so then also there's Fermat's little theorem, which I think y'all have seen before, which is basically telling you that if A is an integer, P is a prime, not dividing A, then A to the P minus 1 is congruent to 1 mod P. And then it has an extension, which is Euler's theorem. So this is Fermat's little theorem. And this is not too hard to prove. There's also Fermat's last theorem, which you may have heard of, about equations like a to the n plus b to the n equals c to the n. But that one is much, much more difficult. And no Olympiad problem should have to require that. At least not nowadays. You know, maybe 100 years from now it'll be standard or something, but not nowadays. That took, you know, really smart mathematicians hundreds of years to prove, whereas this is just, you know, pretty easy by comparison, definitely. You just sort of look at some stuff. Anyway, Euler's theorem is more general because it tells you that, like, if a is a positive integer and then n is a positive integer that is relatively prime to a, meaning their greatest common divisor is 1, then a to the power phi of n is congruent to 1 modulo n. Well, what is this phi of n? Well, it's the number of positive integers between 1 and n inclusive that are relatively prime to n. So, for example, phi of 1 is 1, and for any prime p, you know, 1 through p minus 1 are all relatively prime to p, but p isn't. So phi of p is p minus 1 for any prime p. Meaning that shows you why this is a generalization of this. Because if you take n as a prime number, this becomes p minus 1, and so this will just become p not dividing a when n is prime, and you'll get that for Mathematical theorems. And the proof of this is not too hard. Yeah. And if you're wondering how to compute this in more generality, you can say, like, there's a formula that's known. Phi of n is n times the product over all primes p dividing n of 1 over 1 minus p. So, for example, phi of 168, well, 168 is 2 cubed times 3 times 7. So phi of 168, which is the number of primes dividing, which is the number of positive integers that are at most 168 and are relatively prime to it, would be, we don't count them multiple times, we each just count each prime once, so it's just 168 times 1 minus 1 over 2 times 1 minus 1 over 3 times 1 minus 1 over 7. And this comes out to be 1/2, 3rd, 6/7. It comes out to be 48. 168 times 1/2 times 2/3 times 6/7, so you get 48. And this is, you know, fairly intuitive. It's just like they need to not be divisible by any of the primes dividing n. And so if you just sort of picked at random, each of those would have a probability of 1 minus 1 over p of working out. And so you're sort of saying that, like, the different primes are independent. And this idea about, like, different prime numbers sort of being independent of each other for different moduluses being independent of each other when they're relatively prime to each other is sort of the idea of something called the Chinese remainder theorem, which is not something I will go into I probably will not go into great detail about it today, but that's sort of the idea that the different moduli are independent of each other when they're relatively prime. So, like, knowing what a number is modulo 5 doesn't tell you anything about what it is modulo 21. Or knowing what it is mod 4 doesn't tell you about what it is modulo 45. Or modulo 9 or whatever. And so that's sort of that idea. And as long as I'm mentioning things, I would mention something that's not the most fun thing, but you might as well know about it. It's called Wilson's theorem, and it tells you that p minus 1 factorial is congruent to -1 modulo p for any prime number p. And this is not too hard to prove either. You can find proofs of the results I'm telling you about on the internet, but I don't plan to go over them much today. The idea of this one is basically, I guess I should say something about it since it's somewhat informative. It basically is like you can pair up the residues. Like first, if P is 2, it's just clear. Otherwise, you sort of say that you can pair up all, or I guess if P is 3, it's also pretty clear. Like, so it's the product always. So otherwise, you can sort of pair up every residue modulo P with its inverse, the number that gives you 1 when you mod P, when they're multiplied together. So for example, the inverse of 2 modulo 5 is 3, because 2 times 3 is equal to 1 mod 5. 6 minus 1 is divisible by 5. And so you pair up every number with its inverse, except 1 and P minus 1, which sort of acts like negative 1, stay by themselves. All of the pairs multiply to something that's 1 mod P, so they sort of just cancel out, and then you're left with a 1 and a negative 1, and so you get this. That's, I guess that is the proof, so I guess that is, I am sort of going over the proof bit. But that sort of brings us to an important idea, which is like, how do you know that it has an inverse modulo P? And moreover, if you wanted to find an inverse, how would you do it? And so that sort of relates to our next topic. And again, you can, if anybody has any questions, feel free to ask. But if not, I can keep going. So the question is, like, how would you even find an inverse modulo something? When do they exist? So like, when does a number A have an inverse modulo D? So like, given A and D, how can I find K such that AK is congruent to 1 mod D? So we want to find, given A and D, we want to find K satisfying this. And there are, I guess, a couple of ways you could go about this, but I want to talk about the Euclidean algorithm. So basically, first of all, if D and A have any common divisor, if say they're both divisible by some number B greater than 1, then like B will divide D, and B would divide AK for any K. So if B were to divide D and D were to divide AK minus 1, then B would divide AK minus 1. But then B would divide AK and AK minus 1, so it would divide the difference. So B would divide 1, but we said B is greater than 1. And so that wouldn't be possible. So if this is going to happen, we need their GCD to be 1. So for example, you can't expect to have an inverse of 4 modulo 6, because the GCD of 4 and 6 is greater than 1. So it's not equal to 1. So, since the GCD is 2 of 4 and 6, you don't get an inverse of 4 modulo 6. Because any K you put in here, this is going to be even. And so an even number can't be congruent to 1 modulo 6. But what if their GCD is 1? Now it gets more interesting. So, and this sort of is another question about how can you compute GCDs at all? And so, I mean, one way you can look at the GCD is just to look at the prime factorization and just like look at the powers of the different primes. But what if you don't want to do that? Another way, how could you compute GCDs using just sort of like addition, like just sort of easier operations? And so the answer is the Euclidean algorithm. And it basically uses this idea that GCD of two numbers, say x is less than y, then the GCD of x and y is, or I mean just for any integers really, is the GCD of x and y minus x. Well, I guess I should say x is less than y. Sure. And the reason for this is basically that you can just check that like any number, like if a number d divides x and it divides y, you know, you can say x is kd, y is md, then it divides y minus x because it's, you know, m minus k times d. Meaning, any number that divides x and y divides x and y minus x.
Λοιπόν, πάμε να δούμε το 2x4. Οκ, υπάρχουν... Ναι, υπάρχουν 6 τρόποι. Νομίζω υπάρχουν 6. Πάμε να ζούμε. Πώς βάλουμε όλα μαζί.
Okay,
You can continue.
okay, thanks. Yeah, so basically any number that divides x and y will divide x and y minus x. And so in particular, since the GCD of x and y divides x and y minus x, it will divide, you know, their GCD. So we will have, and there are some properties I'm sort of glossing over as I go along, but or I guess I can just say that it's less than or equal to it. But yeah, if a number divides two numbers, then it divides their GCD. And that's sort of the, like, you know, the GCD, you know, like, you know that if a number, well, I mean, I guess it's, here I would just say, like, since this number divides x and y minus x, it must be at most the greatest common divisor of those. But you can say that it must divide it. Since it divides the two numbers, it divides their GCD, but I don't need that here. Yes?
There is a question like in that the left side, how did B divide AK?
This was sort of in the case of when the GCD of A and D would not be 1. Yeah, I guess I should sort of draw a line in this case if the GCD were greater than 1. Then if, you know, if you took B to be, you know, their GCD, say, then it would divide A, so it would divide A times anything, and it would divide D. So if there were some K making this work, you would get a contradiction. So yeah, I guess that's sort of like two cases. So I guess I should, you know, draw a line to separate them. Does that help? I hope. So yeah, I guess. I hope that helps. So anyway, so about this, this will, you know, divide both of those, so it's at most their GCD. But you can go the other way in that, like, you know, if I say that, you know, if I let D prime be the GCD of x and y minus x, and then I say like x is, you know, r times d prime, y minus x is s times d prime, and since d prime divides x and y minus x, it divides their sum, so, and then d prime divides x and y, so it's at most GCD of x and y. And now we have these two numbers, each of which is less than or equal to the other, so they must be equal. So we get this idea of the Euclidean algorithm. And so you can use this to compute GCDs of things. So, for example, if you wanted to compute, and so in small cases, it can be easier just to compute, just to do the prime factorizations. Let's say like, you know, if you had like, if you wanted to compute the GCD of 63 and 91 with this, well, you can say, okay, that's equal to the GCD of 63 and 28, because 91 minus 63 is 28. Okay. Well, now what? Well, now you can switch them and then do this subtracting again. So then 63 minus 28 is 35. And you just keep going until you get smaller and smaller numbers. 7, and then switch them again. And then eventually you'll just get, if you subtract 7 from 28 3 more times, you'll get GCD of 7 and 7, and that's just 7. Or you could even go once more to 0. And then of course you would just say GCD of 7 and 0 is 7. Because 0 is divisible by anything. But the only number that divides 0 is 0. That's sort of the general rule, but you might want to be a little careful if you say like which numbers divide 0 or what does 0 divide on a contest or something. You might want to be a little careful about that. And yeah, we don't really need to, we don't really need to concern ourselves with that right now. But yeah, and so there's another thing you can do to make your life a little easier, because notice how like we need to subtract 28 from 63, 2 times. We would need to subtract 7 from 28 multiple times. And so like to make our lives even easier, we can sort of let ourselves do multiple subtractions at once, in that you could show, similarly to how I just showed, that like for any value m, we would have GCD of x and y is the same as GCD of x and y minus mx. And so I guess you could say that this is sort of the extended Euclidean algorithm. And so then you could just go directly from 23 to 7 and then, whatever. And so, and I guess it will be, hang on, I'll say something. Basically like, okay, yeah. Basically like, now, what we can do now is we can run this GCD operation and so the numbers, you can see why this operation terminates, because the numbers get smaller and smaller. Right? Without going into too much rigorous detail, just like you must hit something eventually, because it just keeps getting smaller and smaller. I mean, formally, I guess you could say like the larger number in the pair decreases at every step, so it must terminate, because it's always a positive integer. And there's no infinite, strictly decreasing sequence of positive integers. You know, if you keep decreasing a positive integer, you have to stop sometime. If you allowed yourself to go into negative numbers, you could keep decreasing, but we don't do that here. So yeah. And so let's look at our A and D over here. And then if we run this Euclidean algorithm on them, but like let's keep track of how they are expressed in terms of A and D. So maybe we have like some number GC, it's equal to, maybe A and D minus MA, and then maybe we need to switch them. Basically, at each step, you sort of take the quotient and the remainder to be as efficient as possible about it. And yeah, I guess at the last step, I'll say you go to 0 at the, well, I mean, we really don't need to do that. So I guess like the largest number in the pair increases at every step unless you end up with just GCD of the same number with itself, in which case, never mind. Yeah, I mean, like even in that case, it is decreasing anyway. And then maybe we have, GCD of D minus MA, A minus, M prime times D MA. And then you could expand this and write it as like 1 plus m prime minus m prime d, and so on. And you can just keep writing these numbers as something times a, and then like some integer times a plus some integer times d. Maybe the integers are negative, but you can still do that. And eventually you'll get down to 1, and you'll still, because we assume that the GCD is 1, and then you'll end up with, you know, some integer times a plus some integer times d is 1. And so, in fact, this sort of general idea that for any positive integers m and n, you can find some, you know, v and w to make them give their GCD. This is, and you can do this for more than 2 numbers actually. This is Bezout's lemma, and this is important to know. And so this is how we can get modular inverses, because now we can just say x times a is congruent to 1 mod d. And so that's a way to get modular inverses. That's how we know they exist at all. But this Euclidean algorithm, you can run it. You can sort of use this idea to help you not just with integers, but with polynomials. I want to say more about that, but I think I'll do that if I show an example. Yeah, I think let's do some example problems. So, just here, let's do some problems. So here's just sort of an easier problem. This is from a contest at a university. This was problem 1 on a number theory test at Princeton University's competition in 2019. Problem 1 on the Division A number theory test in 2019. Basically, it's just like how many ordered pairs A, comma B of positive integers are there such that their LCM, the least common multiple of A and B, is 6 to the 5th power. So try this problem for a couple minutes. If you think you have the answer, this was a contest. Unlike the IMO, this came from a contest where you only needed to give numerical answers. And so, you know, if you think you have the answer, just like message me, and I will tell you if you have the right answer. And then in a couple minutes, I'll go over the solution. I'll give you all a couple more minutes to try this problem. And yeah, message me if you think you have the answer. I'll give you all like 1 more minute or so, and then I'll tell you all the solution. Okay, so I'm hearing some answers, but so let's see the solution to this problem. Basically, since the least common multiple of A and B, just let's look a little fundamentally. When you have two numbers, just in terms of their prime factorization, say I have P1 times, and let's write, I'm going to allow some prime numbers with exponents of 0 for the sake of saying, like, just to include all the, if I have two numbers, say x and y, let's write out their prime factorizations with every prime number that occurs in at least one of them. So maybe there are some exponents of 0 on numbers that occur on prime numbers that divide only one of the numbers. So let's write it like that. And then basically, on their, what is their least common multiple? Well, it has to be divisible by P1 to the E1 and P1 to the F1. So it's divisible by P1 to whichever of those two is larger. but it doesn't have to be divisible by p1 to any higher power. So we can just say it's, and since all the prime factors are, all the different prime numbers are independent, we can just say like, that's how it is. Because that's just what we need. We need it to be, the exponent of p1 to be at least e1 and at least f1. We need this maximum number. That's what you get. And then just do the same thing for every prime number and multiply them together. And then we don't need any other prime numbers. We don't need to just bring in some other irrelevant prime number, you know, q or something, and tack it on, because that, you know, that doesn't help. So we can just say this number. Okay, so now we know this is equal to 6 to the 5th power. So what is the prime factorization of 6 to the 5th power? It's 2 to the 5th power times 3 to the 5th power. And so there are no other prime numbers that can occur in A or B. And so if we write A is like 2 to the E1 times 3 to the E2, and B is 2 to the F1 times 3 to the F2. And this is sort of assuming that each of 2 and 3 occurs in at least one of them. But actually, you know, even if E1 and F1 were both 0, like this would still be true, because you know, if there were some other prime 0 and 0, you could just take max 0 and 0, and that, like, that doesn't hurt anything. So this will still be true, even if both of E1 and F1 are 0. And now we just need to count, you know, now we're just saying, okay, max of E1 and F1 is 5. And, you know, we know there are no other primes. Max of E2 and F2 is 5. So obviously this is saying they can't both be 0 anyway. So that's sort of, this sort of is a stricter condition. So we're counting, you know, how many ways can we choose E1, F1, E2, F2, so that this holds, and they have to be non-negative integers. And you know, as I said, we don't want them both to be 0, I guess, but that sort of, this includes that. So how many ways do we do this? Well, how many ways can we choose E1 and F1? Well, you can choose E1 to be 5 and F1 to be 5, or you could choose E1 to be 5 and F1 to be less than 5, 4 or 3 or 2 or 1 or 0, or you could choose E1 to be less than 5 and F1 to be 5. So that gives you 1 plus 5 plus 5 ways. So there are 11 ways to choose E1 and F1. By the same logic, there are 11 ways to choose E2 and F2. And now, how do we get the final answer? What do we do with these numbers? Well, we have 11 choices for E1 and F1. Independently, we have 11 choices for the pair E2, F2. So, how do, you know, make the choice for E1 and F1, independently make the choice for E2 and F2, and so that corresponds to multiplying them together. It's like you could write a table with like the choices for E1 and F1 on this side, the choices for E2 and F2 on the top, and then just like look at every intersection in the table as a choice. So the final answer is, you know, 11 times 11. So the answer is 121. So yeah. Does anyone have any questions about that?
Luke, sorry for like the once again, like, can you repeat from the, like how you calculated the 11?
Oh, sure. Yeah, basically it's just that there was one way where they're both 5s. There were 5 ways where E1 was 5 and F1 was less than 5. There were 5 ways of E1 being less than 5 and F1 being 5. You know, just this 1 plus 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. You know, you could just write them down as like 5, 5, 5, 4, 5, 3, you know, to 5, 0, you know, 5, 2, 5, 1, 5, 0, 4, 5, 3, 5, 2, 5, 1, 5, 0, 5. And then just, yeah, that's where the 11 comes from. Any other questions about this problem, anybody?
Can you once also again explain when they become 0?
Oh, yeah, the 0 would just be corresponding to like when the exponent, when the factor would just become like you know, any number, you know, raising 2 or 3 to the power of 0 just gives you 1. So yeah, you could choose like, for example, if I chose 2 to the 0 and 2 to the 5, that would just be like a 1. So like if I choose E1 to be 0 and F1 to be 5, and then if I choose, say, E2, maybe I could say E2 is 5 and F2 is 1, for example, maybe. And this would correspond to the pair A is 3 to the 5th power, B is 2 to the 5th power times 3, for example. So that would be the case where the exponents become 0, because then the prime numbers raised to the power of 0 just becomes 1, and so we just basically ignore it. Any other questions about this problem, anybody?
Sorry, like the confusion again lies on 11. So like can you just list all the order pair elements so that others can like be clear?
Oh, sure. Sure. I guess I'll just sort of get rid of the dot there. Yeah, it's. And so this is sort of the ordered pairs of exponents. And so these are like the possible choices for the ordered pairs of exponents on the 2s. And then separately, we have the ordered pairs of exponents on the 3s. And so basically, like, there's this, you know, fundamental combinatorial principle that like, how if you have some number of choices to do one thing, and you have some number of choices to do some other thing, you know, then you have the product, the number of ways to do both things is sort of when you multiply them together. You know, like if I have 3 shirts and I have 5 different hats, then the number of outfits I could wear is, you know, 3 choices for a shirt times 5 choices for a hat. You know, like I could wear my red shirt and then maybe a white hat, a black, you know, you could just sort of list out all the possibilities and you would multiply them together, and that's how the multiplying the 11 and the 11 together is. Does that help? Maybe should I do a more?
We can also do it from the combinatorics combination. Like separating out 5 and 5, and then for the rest of the ordered pairs, we can do it like from the formula, because many of the Nepalese students are familiar with that kind of formula. So.
Oh yeah, like just sort of maybe I'll. I mean. It's not like any deep formulas are being used here, but basically, like, maybe it would help. Well, here, I'll do an example. Let's just sort of imagine that we replace the 5s by 1, and just ask how many pairs A and B give you the least common multiple is not 6 to the 5th power, but just 6. Well, then more simply, we could say the possibilities for the ordered pair to be of the exponents of 1s would just be 1, 1, 1, 0, or 0, 1, because the maximum must be 1. Meaning one of them must be 1, and they're both at most 1. And so, you know, we can have they're both 2s, or one of them is a 2 and the other one isn't. And similarly, for the powers of 3, you could do the same thing. And so, you know, you could write 6, 6, 6, 3, 3, 6. Or you could write 6 and 2. 6 and 1. 2 and 3. Or no, sorry, 3 and 2. Or you could write 2, 6, 2, 3, or 1, 6. Remembering that any number raised to the power, any positive integer raised to the power of 0 gives you 1. And so this would be, and so there would be 9 pairs that work if we were doing this just 6 case. So does that, and so these would be the 9 pairs that work in this grid here. So, so does that help answer questions, or are there still more questions?
Oh yeah, that helps.
Okay, good. So if there are no other questions, I think I wanted to show, I had planned, I wanted to show at least one other example. And so, let's see. Man, there were a couple of examples I had wanted to show. Is it okay if this lasts over an hour? I mean, and people are free to leave if they have to, or if they need to leave after, you know, an hour, of course. But is it okay?
Yeah,
if
it's
it
no
goes
problem
over an
at
hour? Okay,
Yeah,
good.
it's
Okay, good. There are definitely a couple more examples I wanted to show. And so here's a problem. Here's another problem. This is an example of how a use of a pretty simple use of modular arithmetic, but definitely a use of it for this next problem. And it shows how, like, if you have an equation, it can be useful to take a specific modulus. So this next problem comes from the USAMO, the United States Math Olympiad. But it's pretty old. It comes from like 1979. So this is pretty, you know, this is easier than a modern Olympiad standards, but still it's, you know, it's definitely an instructive problem. And so the problem, I'm modifying to modify the problem slightly, but it's, you know, the same, it's the same idea of the solution, which is basically like prove that there do not exist integers x1, or I'll call them a, A1, A2, up to A sub 14, such that, so prove that you can't take 14 integers such that their fourth powers, whenever you raise all of them to a fourth power and then add all their fourth powers, they sum to 1,599. So prove that you can't take 14 integers such that when you raise them to the fourth power and then add them all up, you get 1,599. So yeah, that's the problem. So spend a couple minutes thinking about how modular arithmetic might be useful, and then I can show y'all how to do this problem.
Are the integers conjugative or?
No, they're allowed to be. There could be, you know, they could skip around. There could be repeated integers. You would be allowed to repeat them. They don't have to be consecutive. They can just be. Yeah, I'm just using these sort of subscripts as sort of a way to just tell you how many there are. I could have called them A, B, C up to N, because N is the 14th letter of the alphabet. But I think it's, you know, you shouldn't have to like manually go through the alphabet and say which position is that, you know. So yeah, they have freedom to be any integers you want. So I'll give y'all another minute. Seems like someone has already gotten the right idea. So yeah, I'll give y'all another minute. Okay, so what does modular arithmetic have to do with this equation? Well, it can be useful to pick a specific modulus. And so, someone suggested take modulo 16. And yes, that is indeed what you want to do. Because it turns out to work really nicely. Because first of all, this number 1599, that's 1600 minus 1. 1600 is a multiple of 16. So this is congruent to negative 1 mod 16. So it's congruent to 15 mod 16. However, what is any, whenever you take an integer and raise it to the 4th power, what do you get? Mod 16. Well, if n is even, then 2 to the 4th divides n to the 4th. That's 16. So n to the 4th is 0 mod 16 if n is even. What about if n is odd? Well, you could just say, take 1, 3, 5, 7, 9, 11, 13, and 15, and just raise them all to the 4th power and check what you get mod 16. But that would be a little, we don't have to do that much work. But like any odd number would be congruent to one of those modulo 16. So you could do that. But we don't have to do that much work to check what happens. Because notice something. If we just look, let's focus for a moment modulo 8. We can see something interesting. Any square of an odd number, because any odd number is congruent to 1, 3, 5, or 7 mod 8. Any square of an odd number is congruent to 1 mod 8. Because these are the only cases, and these are all congruent to 1 mod 8. You could see that just by saying like 2k plus 1 squared. You can do some algebra, just, you know, it's 4k squared plus 4k plus 1. That's 4 times k plus 1 plus 1. And now, one of these numbers, k and k plus 1, must be even. They can't both be odd, so one of them is even, forcing this product to be even. Forcing this product to be a multiple of 4 times 2, 8. So any odd number squared is 1 mod 8. And now, if we take an odd number squared, so now if we take n as an odd number and then raise it to the 4th power, what do you get? Well, that's squaring it and then squaring it again. So n squared is some number 1 mod 8. And then modulo 16, this gives us, you know, 64k squared plus 16k plus 1. Modulo 16, this cancels because it's 16 times 4k squared. This cancels, so you're just left with 1. So any odd number to the 4th power is some 1 mod 8 number squared. And so it's 1 modulo 16. So any odd number to the 4th power is 1 mod 16. And notice, actually, this is actually stronger than what we would get if we applied Euler's theorem. Euler's theorem would tell you that if n is an odd number, if n is an odd number, then it's relatively prime to 16. It doesn't have any divisors in common with it. And so Euler's theorem would tell you this. But actually, phi of 16 is 16 times 1 minus 1/2, so it's 8. So Euler's theorem tells you that any odd number raised to the 8th power is 1 mod 16, but it doesn't tell you about when you raise it to the 4th power. So actually, this is somewhat more powerful, because you can get this from this. You can go this way if you just square this and then look at it. But so this is more powerful looking at some explicit cases. And so what do we have here? We have if n is even, its fourth power is 0 mod 16. If n is odd, its fourth power is 1 mod 16. Meaning, any integer n, any n that's an element of the set C, the set of all integers, and its fourth power is 0 or 1 mod 16. But now look, if we just take this equation modulo 16, we would then get some equation of the form 0 or 1 plus 0 or 1 plus and so on, 0 or 1 is congruent to 15 mod 16. But then this, like, the sum of 14 things that are 0 or 1 would be 0 or 1 or 2 or so on up to 14. But then you would have 1 of 0 through 14 congruent to 15 mod 16, which is not possible. So that would be a contradiction if this existed, so they don't exist. The end. QED. And so this, we sort of, and this was using the idea of proof by contradiction, where if you want to show that something is impossible, like basically, if you want to prove that something is the case, you sort of assume the opposite of what you want to prove and show that that would lead to a contradiction, meaning that what you wanted is the only option. So here we wanted to show that these numbers can't exist. So we said, okay, what if they did exist? And then we got this contradiction. And so we said, okay, assuming that they existed gave us a contradiction, therefore they don't exist. And so we say, we're done, QED. This is some Latin that means which was to be shown. Basically, we're done with this problem. So are there any questions?
Can't we use other modulo? Like 3, 5?
Well, that, I mean, it would depend on the problem. In this case, I don't know how that would work because, like, you would have, like, having so many numbers gives you a lot of freedom what to do with. Like, so in this case, like, I don't see how you, because, you know, if we said 5, if we took modulo 5, say, then, like, you would actually have the same thing by Fermat's little theorem. That there would be 1, 0 or 1 mod 5. And then this would be 4 mod 5. But then, like, adding up 14 things of the form 0 or 1 can give you, you know, 0 or 1 or 2 or 14. But then, like, we would get something like this. And this is not a contradiction. Like, we need to make sure that the final thing we get actually gives us a contradiction if we want to prove that something is impossible. Or maybe not that it gives us a contradiction, but just that it tells us some information. But in this case, we definitely wanted to get a contradiction. So, like, you wouldn't get a contradiction out of this, because this, you know, like, you can choose one of these to make this work. You could choose 4 or 9 or 14. But this does give you a contradiction, because none of these numbers are congruent to 15 modulo 16. And so, you know, you want to, but of course, you know, if you were trying this problem, if, you know, if this showed up on some contest, like, you could just try a bunch of different things until you found something that worked. So, you know, maybe you tried modulo 5 and said, oh, that doesn't work. And then you tried, you know, some other moduli. And then you tried modulo 16 and you said, hey, that works. And then you would just be like, okay, I found something that works. I'm done. Let me write up my proof. You know. So, you know, you can try a few things and, you know, maybe you don't stumble on the right thing right away. So yeah, any other questions? Okay, in that case, if there are no other questions, oh, a solution. Someone asks if there is a solution by inequalities for this problem. Well, I mean, yes, you could. Well, not. I mean, you could say that since any fourth power of any integer is non-negative, any square is non-negative. This is the so-called trivial inequality, meaning any term must be at most this, because all the other terms are non-negative. So the only options for terms are 0, 1, 2 to the fourth power, 3 to the fourth power, 4 to the fourth power, 5 to the fourth power, or 6 to the fourth power. Like any other option would be too big, because 7 to the fourth power is 2401, which is too big. And other, you would get it even bigger. But like, that would be a lot of cases to check. And you still might end up taking some modulo. And so like, this is going to be like sort of the simplest way of doing this problem, or at least that I know of. Or at least like the easiest way once you're familiar with this modulo stuff, probably. But at least some approach of this form of looking at moduli, of looking at modulo 16 and doing this would be the easiest way. Some version of this solution would be the easiest way, but that could, other ways might be messier if they work at all. Any other questions? Okay. So yeah, someone asks to move on to the next problem. So yeah, let's move on to the next problem. So this one problem, this was again from a contest where you don't have to give where this contest also didn't require proofs. It just required numerical answers. And so this was on the AIM, which is a contest that leads up to the USA Math Olympiad. And this is from like 1985, I think. And so the problem is basically like, if n is a positive integer, what is the largest? If n is a positive integer, what is the largest possible value of the GCD of n squared plus 100 and n plus 1 squared plus 100. I think this will probably be the last problem we do in today's session, and then tomorrow's session I'll show more solutions to problems from that list of problems that I think is going to be sent out. And some of those are pretty challenging problems, but I want to show, I'll want to hopefully show at least some examples of like more recent Olympiad problems next time. And so you'll have, much more time to work on them in just a few minutes. You'll have like, the full day's worth of time. So hopefully that'll, help you get more out of it. For tomorrow's session. But yeah, I think this will probably be the last problem of today's session. So yeah, try this problem for a couple minutes. Oh, someone asks, is the answer necessarily an integer? Well, for any positive integer n, these will be positive integers, and so their GCD will be a positive integer. It's not immediately obvious why there is a largest possible value. Maybe you might think, oh, maybe this can just be as big as we want. But as it turns out, there is an upper limit to how large it can be. Like it turns out there are only finitely many possible values, and one of them is the largest. So yeah, it turns out that the answer is an integer. I'll give you all maybe one more minute. Someone says it may be 1. There are a lot of n for which this equals 1, but the answer turns out to be greater than 1. So yeah, I'll give you all another minute. So let's see the solution to this problem. And so this is going to sort of use an idea that's sort of like the Euclidean algorithm, except not exactly, but sort of the Euclidean algorithm tells us, it's something like the Euclidean, it's something like that. It's the same basic manipulation, sort of, mostly. It's mostly the same basic manipulation. It's the same intuition, sort of. In that, like, the Euclidean algorithm is like, you sort of use this GCD operation of like, subtract and like, subtract by an appropriate multiple, sort of, to get from bigger things to smaller things. And you sort of use these operations to sort of keep making it smaller. And so here, instead of big numbers and small numbers, we're going to look at it in terms of polynomials, in which a polynomial of higher degree is sort of bigger than a polynomial of lower degree. So this is a polynomial of degree 2, and this is a polynomial of degree 2. That's sort of the coefficient, the highest coefficient of any term. If you expand this out as like n squared plus 2n plus 1 here. The highest coefficient of the term is 2. And so we're sort of going to use that to sort of get rid of some terms. So let's look at this. This GCD, for any positive integer n, this GCD, well, it's equal to the GCD of n squared plus 100, and the difference between these two numbers, which is just n squared plus n plus 1 squared minus n squared, so that's 2n plus 1. And now what? What do we subtract off by to make the n squared go away? Well, we should, we want to get rid of, you want to get rid of the n squared, you want to get rid of the n squared. But how do you know how many times to subtract off 2n? And so to avoid getting into some messy stuff with like, oh, is n even or is it odd or whatnot, let's just say, since we don't really, for the moment, I'm just going to do some less than or equal to stuff in that, like, this is at most the GCD of twice this and this, because this divides this and then this is the same thing. And now I can say, like, I can say this. I'm not being, like, basically I'm sort of subtracting a multiple, and then I can also flip the sign, because it, we don't care too much about positive versus negative. We're only just concerned about, the divisors. And so this is sort of the same idea of take a multiple of this and subtract it from here. Because, 2n squared, whatever this GCD is, it divides 2n squared plus 200. It divides 2n squared plus n because it divides 2n plus 1. So it divides 2n plus 1 times n, which is 2n squared plus n. So when I subtract those, I get this, n minus 200. And, you can go the other way by the same old argument. And this might be positive, negative, or 0, but it's fine. The manipulations are still valid. But yeah, you might want to say something about that in an Olympiad. If you ever have to do manipulations, just in case they might be a little picky about that. And so you might want to say, the GC, 0 will work with 0 just like any other number, saying, 0 divides only itself, but any number divides 0, So anyway, once we're to this point of GCD n minus 200 and 2n plus 1, well now, I can just subtract 2 copies of this, 2n minus 400 from 2n plus 1, and get GCD of n minus 200 and 401. Great, which is at most 401, because it divides 401. Okay, so this GCD, we did the Euclidean Algorithm a bunch to get that it's at most 401. Can it be equal to 401? Well, what's the most natural choice? Because this is sort of almost equality, right? So if I take some n to make this happen, say I take n is 200, forcing GCD of 0 and 401, which is 401, then this turns into equality. If I take n is 200, and then this is equality, this is equality, this is equality. The multiplication by 2 didn't change anything, you can see, because it's 401 here. And so, you just get equalities all the way through. Also, you could just check that it works. 200 squared plus 100, which is, easy. And you might want to just do that anyway, or maybe. And in this case, you can just do it anyway, just sort of to check that you did it correctly. This is 40,100, which is 401 times 100. 201 squared plus 100 is 40,501, which is 401 times 101. So yes, the GCD is 401 in this case. And so notice what we did here. This is sort of just an important this is sort of an important general thing for whenever you have a problem that says, what is the largest possible value of such and such, or what is the smallest possible value of such and such? There are two parts of it. There are, once you know the answer, there are two parts to proving that 401 is the answer. We proved that it's always at most 401, and we proved that 401 is possible, because the GCD in this case is 401. And so that is the answer. 401 is the answer. But yeah, if we only did this part, then we wouldn't know for sure that 401 was a possible number to get at all. You have to check. And if we only did this part, we wouldn't know that maybe it could be much bigger for all we knew. So when you do a problem like this that says what's the largest possible value, you need to sort of, there are two parts, the bound to show that it's at most that, and the construction to show that it's a possible value. And similarly, if there were a problem that as small as possible. That's just sort of a general lesson about problems like this. So yeah, that's how that you can sort of think about the Euclidean algorithm as being useful, even in not so obvious cases. So are there any questions about this problem? Feel free to ask a question if you have a question. So yeah, if there are no questions, I guess we'll stop here for today. So thank you for having me. Thank you to all the students for your participation. Thanks for your active participation. Thanks to the hosts for having me. And so I guess I'll see you tomorrow at the same time for another session. And so, you'll want to try the problems that are sent out, but, don't worry if you can't solve that many of them. These are, if you find, if you find them should be pretty hard, they're definitely not easy problems. So don't worry. I'll be showing solutions to some of them. There are a lot of problems on the list, so, we probably won't get to all of them tomorrow, but maybe some of them is the idea. So yeah, thank you all for coming.
Thank you.
Thank you for coming.
Thank you
very much.
Thank you.
That you came in such a short notice and you taught us about number theory, so vast topic and many topics and many questions. Thank you for that and hope to see you soon tomorrow.
Thank you. See you tomorrow.
Thank you.